Okay, so I had someone ask me for help with this problem. It's a physics 1 problem. Doesn't really require anything other than some physics. If you can always DM me at my Instagram, which I'll put here, the underscore physics underscore tutor. I'm a lot better explaining things, I think, over here because I have a tendency to the way I like to point things out, I prefer pointing at them, but at least now I can highlight and stuff like that. And this also goes along nicely with the Physics 1 series we're doing. Obviously, this isn't where we're at in the series, but we will at some point, and at least it's something. So let's go ahead and get started. It says, during a St. Patrick's Day celebration, for reasons we will not discuss, a person is driving a car of mass m, speed v, in the wrong direction out of the physics department parking lot in the positive y direction. At the same time, a law-abiding citizen in a pickup truck of mass m is traveling at an unknown speed on Pine Street, which makes an angle theta with the x-axis. The car and the truck collide and stick together. The fused direct is skidding in the positive x direction along the horizontal road surface for a distance d until it comes to a stop. Drive an expression for the coefficient of kinetic friction mu between the wreckage and the road in terms of little m, big M, Vd, theta, and constants. You may use, without proof, the normal force magnitude is equal to the weight magnitude. Okay, so I'm going to do this a little differently than the way I was actually explaining it to her earlier, because I think this might make more sense. Let's start with our momentum. So momentum's a vector, and we'll start by looking at momentum in the y direction. So momentum initial y direction is what? Let's just go ahead and write it down, actually. Well, in the y direction, we have the drunk driver, so that's going to be little m times, and I really don't like this notation, so I'll call this m1, v1, m2, v2, v3. That's what I'm going to do. m1, v1 minus, it's supposed to be big M2, v2. However, if we want just the y direction, this is our theta. So this is sine of theta, which is equal to 0. Now, we can solve for the velocity of the pickup truck by just moving it over. And dividing everything out. Okay. So cool, we know something. Now, we're going to do the same thing, but look at momentum. Remember, momentum is a vector. And the x direction. Now, if we look in the x direction, remember, this is from where the cars collided, so this is right here. And obviously, there's no y momentum. And in the x, well, the drunk driver is not doing anything in the x. That's just this part right here. So that's going to be m2 v2 cosine theta is equal to what? That'll be m1 plus m2 v3. Okay? Now, this v2 we just solved for. That was here. So, I could say m2 times m1 v1 over m2 times sine of theta times cosine of theta equals m1 plus m2 times v3. Okay, and we can just cross these out, and divide over by m1 plus m2. So m1 v1 sine over cosine is cotangent. And then we're going to divide by mass 1 plus mass 2 to get our final speed, v3. Okay? Now, I'm going to use work and energy. So we know from the work energy theorem, work is equal to your change in energy. Okay? We also know work is equal to our force times delta x, but I'm going to call it d because that's what they called it in the problem. Now, we want to make note that this is looking at when they collide until they get to rest. Okay? So, if we think of our change in energy being our energy final minus energy initial, what we would do is we would say, all right, our work, let's just keep it as is. Our force times distance is going to be equal to our kinetic energy. There's no real potential, it's all moving. Kinetic is 1/2 m, which will be m1 plus m2, that's the mass of them together, times our velocity 3 squared. Okay? So we want to know, well, first off, let's look at our forces. So if we look at the top, our normal force is equal to our weight force. So our normal force, we know, is equal to mass times gravity. Now, what we're looking at here is our force due to friction. So with work and energy is not conserved here. So we would say our force, which our external force, is going to be the force of friction. And the force due to friction is our normal force times our coefficient of friction. So this is really normal times mu k times distance equals 1/2 m1 plus m2, and then v3 we solved for. We just have to square it. So that's going to be m1 plus, or I'm sorry, not plus, times v1 cotangent theta, all divided by m1 plus m2 squared. That's our velocity. And our normal force is equal to mg, so I can replace that with... Now, I should have actually been a little more careful here because this should be m1 plus m2. So instead of normal, I'm going to say m1 plus m2 times gravity times our coefficient of friction times the distance traveled is equal to 1/2 m1 plus m2 times m1 v1 cotangent theta over m1 plus m2 squared. And you can probably see that this drops with this, and we get g mu naught k times d is equal to 1/2 m1 v1 cotangent theta all over m1 plus m2 squared. And I don't even remember what were we looking for. The coefficient of friction. So then we just have to divide. 1 over 2g times the distance times m1 v1 cotangent of theta all over m1 plus m2 squared. Okay. And I think that's everything. Let's see. We know gravity is a constant. We don't have to worry about that. It wanted us to express it in terms of D. D is there. Let's see. We have mass 1. Is it mass 1 or mass 2? I think this is supposed to be the big M. I should have just kept it the way it was, but I'm pretty sure this is supposed to be big M. And then this is big M plus little m. Or did I get that backwards? No, I think this is actually... Let me see. This is coming from here. Where'd that come from? Okay, I think this was actually... Yeah, V1. Okay, so V1 means this will be little m. I can just, I guess, call this little velocity or whatever they called it. And this would be big M plus little m. So let's see. We have our masses, we have our velocity, our theta. Perfect. So we expressed this in terms of everything we need to know. I'm going to do a quick run back. So we started by breaking our momentum into different sections. And we said that our momentum in the y direction, that's what we looked at first. And we solved for our velocity. Velocity for 2, which was the unknown speed of the truck guy. Then we looked in the x direction and found the final momentum where the two cars were together. Then we used that for our work and energy theorem. Substituted our work with normal, or m1 plus m2, mu naught mu k times d. Substituted our velocity in, and then we solved for our constant. And there we go. That's everything.